Jupiter is the first of the gaseous giant planets. In contrast to the inner planets, which are small, dense and rocky, the outer planets are huge spheres of gas without solid surfaces. Jupiter is the largest planet in the solar system, being more massive than all the other planets put together. The features of Jupiter's outer atmosphere are vivid and constantly changing. The most noticeable feature on Jupiter is the huge oval shape known as the Great Red Spot. This spot is an anticyclone or high-pressure system that's been visible from the Earth for over 300 years. Similar high-pressure systems occur in the Earth's atmosphere, but last for much shorter periods. The Great Red Spot leaves a trail of turbulence in its wake. Atmospheric currents traveling at high speeds around the spot produced this series of eddies and whirls.
When Voyager got up close and we looked at the time-lapse movies of the atmosphere in motion, things were changing every day. Little storms would pop up out of nowhere and then get ripped apart, dispersed all in a day or two. And that made the mystery of the Great Red Spot and those other large spots even deeper, because how could they last for so long in the midst of all that chaotic motion? It was a startling discovery.
We expected, quite frankly, the satellites of the outer solar system to be quite bland and geologically lifeless. As we flew closer, Io looked less and less like anything we'd ever seen. The impact craters turned into irregular dark patterns, and the colored patches, red, yellows, painted on the surface. As a matter of fact, as we flew closer, we saw nothing at all that resembled an impact crater. Voyager 1 discovered 11 active volcanoes, and 9 of those were still active when Voyager 2 returned 4 months later.
I think the event in the mission which really altered our view and our expectation for the rest of the mission was the discovery of the volcanoes on Io. That was such a dramatic and unexpected thing to find that it really told us that we could no longer be complacent. We could no longer expect to understand or anticipate what we were really going to see.
The next moon out from Jupiter, Europa, has a very smooth surface of ice. The long dark streaks are thought to be subsurface cracks in the ice.
In a solar system full of amazing planets and moons, Jupiter's moon Europa stands out. Sandwiched between its icy skin and mantle, there's an ocean, twice the volume of all of Earth's oceans. The Galileo spacecraft returned images of Europa that revealed a strange variety of icy structures, some created by blobs of warmer ice that rise through colder ice. Europa generates heat inside. How? It fluxes as it's tugged by Jupiter's gravity.
Just like the Earth's oceans have tides because they're pulled by the moon's gravity, Europa should have a tide because it's pulled by Jupiter's gravity. And Europa, as it orbits, gets a little closer and a little farther from Jupiter. So when it's closer to Jupiter, it will be stretched out more. When it's farther from Jupiter, it would contract more. So in a similar way, this flexing of Europa as it orbits around Jupiter is generating heat and keeping that ocean going.
It may even be hot enough that if the mantle encounters water, it might create black smokers like we see on Earth's ocean floor, an environment in which primitive organisms might be able to survive.
I would certainly say that Europa has the most potential within our solar system for life outside the Earth. Other icy satellites are candidates. Mars is a candidate too, and you might get a different opinion from a different scientist. But based on what I understand about the icy satellites, Europa seems very promising for microbial life today.
In contrast to Io and Europa, the surface of Ganymede is very old. This is indicated by the number of impact craters that appear as white spots on the icy surface. It's thought that the various colored bands represent regions of different ages. The dark area on the right is thought to be the oldest region. Callisto also has an icy surface with many impact craters. The large basin visible on the right was caused by a huge meteorite impact early in the Moon's history. Concentric rings spread out from the impact site for many hundreds of kilometers in all directions.
If we look at Callisto, it's one of the most heavily cratered objects in the solar system, virtually saturated with impact craters. When we looked at Ganymede, we find two kinds of terrains. One is a terrain that looks very much like Callisto, but in addition, Ganymede has a very complex intersecting network of faults in a younger terrain, which has evidently welled up from the interior and replaced this old cratered terrain that's so similar to Callisto. In the case of Europa, we see yet another style. We see gargantuan fault patterns in which this ocean has frozen repeatedly, broken open, and fluids float up to the surface, producing dark puddles of material within the faults. These are then broken again, so there's intersecting and cross-cutting networks. There were two small satellites discovered at Jupiter. One of them found orbiting just outside a very thin, tenuous ring of material that was discovered at Jupiter.
The imaging team members planned one single photo, an 11-minute exposure that would be taken as the spacecraft plunged through the equator plane of Jupiter. And it just so happened that there was a ring there. It's dusty, and there seems to be no indication of water or ice within the ring, so it's probably made out of rocky material.